Good morning. Here are yet again for another lovely session of CENG 3325 Structural Analysis. Today we're going to be looking at the topic of shear and bending moment diagrams of frames. So I want to discuss shear and bending moment diagrams of frames. And this is going to build on what we've seen previously for shear and bending moment diagrams of beams, and then also in terms of what we've seen in terms of internal joints in structures. So shear and let me call them maybe perhaps V and M diagrams. V and M diagrams for frames. V and M diagrams for frames. So the big idea here is that whenever we cut a member, or there'll always be internal forces revealed. And for frames, the same thing is true. So the main idea, when cutting a frame at joints, or when cutting a frame, internal forces will be revealed. Are revealed. And to get the shear and bending moment diagrams of a frame, to get V and M of a frame, we are going to cut it at the joints. Cut the frame apart at the joints. At the joints. So I want to discuss the different types of joints, and we have seen this a bit before, but I want to do a bit of a review. Review internal joint types. And we could talk about an internal roller, but I'm going to focus mainly on a pin and a fixed joint. Or I should probably just say joint for internal forces, because joints imply that it's internal. Joint internal forces. So the two ones are going to be pin and a pin joint and a fixed joint. So we'll have pin joints. And we'll also have a fixed joint. A pin joint and a fixed joint here. So for a pin joint, this will be indicated, of course, by a pin or a circle connecting two individual members. Something like this. And what will a pin joint transfer? Let's say you have joint A here. Let's say we call this joint A. What will that pin joint transfer? Will it transfer moment? Exactly, it'll transfer everything but moment. So if I then go and do an exploded view of this, showing the internal forces here, I'm usually going to isolate this, and I could maybe show the pin. I can show the pin if I want to, and but it would just as easily, I could just as easily show perhaps something like this. There are different ways we could draw this. We could draw the pin as its own object, or we can just draw it kind of like this, with our two member ends here. And then if I label the forces, I would have something like this. AX, AX, and AY, and AY. How did I know to make this one up? How did I know to make this one pointing up? Trick question, I didn't. I just guessed. I didn't know which way this was going to be pointing. It doesn't really matter. You can assume either direction initially. If we solve for this and get a negative number, we just know it's going in the opposite direction. However, what do I have to do about this one and this one? They have to be equal and opposite, yes. So in other words, if this member is pushing up or is experiencing upward force, this member must be experiencing a downward force. So that's the basic idea here. Then if we have and the same thing with the x direction here. And a fixed joint will of course be indicated by simply one member going into another. Like this here. And then if I draw this in exploded view, I would have this here and I would have this here. And I'm going to have three internal forces, the same as a pin joint, but with a moment also being transferred through the joint. So I'd have an AX, an AY, then let's see, sorry, not that. Let me do it more like this, sorry. AX, AY, and then also an MA. The moment being transferred through joint A. And an MA. Then an MA in the opposite direction. Then an AX in the opposite direction. And an AY in the opposite direction. Here. Any questions on that? So again, pin joints will transfer through both will transfer a horizontal and a vertical force, and a fixed joint will transfer a horizontal force, a vertical force, and also a moment. Okay.
The direction of the moment on the right.
Mm-hmm. Oh, how did I know that? I didn't. The answer is the question is, how did I know the direction of the moment on this one here? I didn't. I guessed. But I do know, however, that if this one's experiencing an end moment that is counterclockwise, this one must be experiencing an end moment that is clockwise. Again, it all comes down to equal and opposite. Whenever you cut a joint and you reveal an internal force, the two different members are going to be experiencing equal and opposite forces. So it all comes down to Newton's third law, equal and opposite forces. Does that make sense?
Okay, I didn't use the right word. I think I meant orientation, but since it's just clockwise or counterclockwise.
Oh, yes. Counterclockwise and counterclockwise, yes. Okay. Let's see here. Now. Okay, so there is that. And I think maybe I'll work through a few examples. And I think I'll put together later a video on internal determinacy. Okay. So I want to put together a video, or not a video, a short example here. Let's do an example 1. So I'm going to have any questions? Okay. I'm going to have a frame here. And this is going to be a relatively simple frame. And this is actually going to be a statically determinate frame. An externally statically determinate frame, I should say. And I'm going to have it like this. So I have a pin joint here and a roller joint here. And I'll call this joint joint A, and this joint joint B, and this joint joint C. And this is given, and I want to find the V. Let's also get the A, V, and M diagrams. And the A diagram is a diagram of the axial force. Now, of course, we do need to find the loads on here, and we do need the geometries. So we're also given the geometries. The width of this thing is going to be 10 feet. And then we're going to have 2 loads on here. Well, horizontal loads. Let me put the loads in, but then I'll put one more geometry or one more dimension line on here. So let's put a 15 kip point load to the right here and a 10 kip point load to the right here. Then a distributed downward load of 4 kips per foot. Of 4 kips per foot. All right. right, and then the total height of this, or the other dimension lines, I'm going to have, it's going to be 4 feet from here to here, and 4 feet from here to here. So this thing in total is 8 feet tall and 10 feet wide. So let's go ahead and get this. Now, to speed things along a little bit, I am just going to do a, I'm going to give us the reactions first. And that should be fairly straightforward. Solution. So 1, get reactions. Or get external reactions, I should say. And for us, for this problem here, that's relatively straightforward. For more complex ones, where you have more than 3 external forces, we actually will have to break it up before we can even find the reactions. But here, this is very trivial because I only have 3 reaction forces, an X reaction force at A, a Y reaction force at A, and a vertical reaction force at C. So that should be fairly trivial to get those reactions. So drawing out I'll go ahead and draw out a combined free body diagram, but if you work through the equations of statics, you will get the following reactions. Not a blank page, you'll get the following reactions. So here, you'll get these reactions as shown. We'll have an AY, this is going to equal 4 kips. And AX, we can see where that's going to come from very easily. That's just going to be 15 plus 10. And so AX is going to be 25 kips. Then we'll have our 10 kip lateral force to the right and a 15 kip lateral force to the right. Then we'll have our downward force along the top of 4 kips per foot. Our distributed load of 4 kips per foot, and a reaction CY equal to 36 kips. And this is our overall free body diagram of our combined structure. Oh, I don't want that. And I will go ahead and just duplicate the dimension lines so I have them on the same diagram. So this is going to be 4 feet, 4 feet, and 8 feet. All right, questions on that? Again, finding those is, 10 feet. What's 2 feet among friends? 8 feet, 10 feet, 3, 4, 5 triangle, something. Well, that's actually not a 3, 4, 5 triangle, but anyway. So the next thing I'm going to do is to break the structure apart. The next thing I'm going to do is break the structure apart and look at what internal forces are revealed. What kind of joint is this? It's a fixed or a rigid joint. Same things, same words for both, but it's basically a fixed or rigid joint, which means it's going to transfer a vertical force, a lateral force, and a moment from one member to the next. Okay, so I'm next going to draw this in an exploded view. And I'm going to draw a combined free body diagram of here. So I'm going to do this on one big slide, I think. Exploded view free body diagrams. So this is step 2, exploded view free body diagram. So if I have my one member here, my column here, and my beam here. So I have a column here and a beam here. And let's look at the, let us consider the forces here. I'm going to have let's say a 10 kip force here. That's not changing. I have my 25 kip force here and my 4 kip force here. And my 4 kip force here. And then I have my 15 kip force. External load, yes.
Doesn't the 25 go the other way?
Oh, thank you. Yes, that was going the other way. Thanks. Yes, 25 kip going that way. Then I'm going to have a BX force. I'm going to have a BY force. And I'm going to have an MA. And I could have assumed these going either direction, although I just decided to be a little bit smart on this, starting on this end, because I know, just looking at this, that BY is going to have to be going down. If we look at our equilibrium here, the only vertical forces on this are both this 4 kip force and this BY force. So in fact, I can actually just go ahead and say, oh, BY is going to be equal to 4 kips as well. I know that. Oh, and BX, look at this. BX is going to be equal to what? It's going to be equal to 0. BX is equal to 0. I already have 10 kips and 15 kips going to the, I have 25 kips total going to the right, 25 kips total going to the left, and so BX has to equal 0. Then in turn, I would have a BX over here, but again, in this case, we already know it's equal to 0. And then I would have a BY pointing upward, and we know this one is equal to 4 kips. And then I have an MA. I just went ahead and assumed this one was acting counterclockwise, which means I'll assume this one is acting clockwise. So I assume this one is acting counterclockwise, and this one it will then act clockwise, although I could easily assume the other direction. Then I'll still have my distributed load here. I'll still have this distributed load of 4 kips per foot, and a vertical reaction of 36 kips. So I'm going to go ahead and do maybe a sum of moments. Oh, and I would like to have my joint labels. This is joint A, B, and C here. Okay, so let me go ahead and then do a sum of moments to actually get the moment. And I'm going to do a sum of moments on this piece here. We could do it either way, but you know what? It's going to be easier on this one because it's going to be easier on this one because then I won't have to deal with the distributed load. Although it wouldn't be that much more difficult on the on the beam as well. It's not like it's a fun parabolic load or something like that that you definitely don't have on your homework. So anyway, so there's going to be a moment. I'm going to do a sum of moments about A is equal to 0, and that will lead to. That's going to lead to the following. I'm going to have negative 4 kips. Wow, that's a really bad equal sign. That's going to equal negative 4 kips negative 4 feet, sorry, times 10 kips. And this is 4 feet, and this is 4 feet so we can remember that as a reminder. Negative 4 feet times 10 kips. And then here, let's see here. And then minus 8 feet. Minus 8 feet times 15 kips. Minus MB. Oh, actually, sorry, this should be MB, not MA. Minus MB. MB. Here is equal to 0. And so again, I'm taking moments about joint A here. So when I sum moments about A, this 4 kip force, this 10 kip force is generating a negative moment about there. And let's see here. And my 8 foot away force, my 15, that's going to generate a a negative moment. So I think that should actually be a positive here. That should be a positive. Sorry about that. And we get that the MB in turn is equal to 160 kip feet. MB is equal to 160 kip feet, counterclockwise. 160 kip feet. Does that make sense? Yeah, that does. Okay, 160 kip feet. Because this would be 15 times 8 would be 120. Yeah, so 160. Good. Okay. Okay, so the next thing I'm going to then do is find the shear and moment diagrams. And this one is actually fairly straightforward. So let me show you what the shear and moment diagrams and A diagram would look like. Well, the only thing that will have an A diagram is the column, not the beam. So here, then let's get the combined V and M diagrams here. Actually, I think I'll do this on the next slide. So we have that, and let's think about this. Or do I want to do this on this slide or the next slide? I'll do the next one. So V and M diagrams, or A V and M diagrams. So I'll have my structure here, and this is going to be created just based off of the free body diagrams, and I'm sort of creating this using the method of inspection. So I'm going to go ahead and show the free body diagram of this. I have my 4 kip force and my 25 kip force, my 25 kip reaction. And I'm going to have my 10 kip force and my 25 kip force. Then I'm going to have a downward distributed load of 4 kips per foot. So a distributed load of 4 kips per foot. And an upward reaction of 36 kips. And then I'll just go ahead and keep the dimensions on there as well. This is going to be... Huh? 25. Yeah, that's a little typo. Sorry, that should say 15. Yes, thank you. Here. There's a few errors in my notes here. That's not good. 15 kips. That inspires confidence. So let's go ahead and put down the dimensions. That's 4 feet and 4 feet, and then a total length of 10 feet. 10 feet from here to here. Okay. Now, I'm going to get these by inspection, and the first one is going to be the axial load. So going back to this free body diagram, I know that there is, the only axial load on this is the 4 kip vertical force. So my A diagram is just going to be constant. And I'm going to draw this along the line, along the orientation of the member. So, actually I probably should have drawn this a little lower, but that's okay. Here, so for my column here, I'm going to call this A in kips, then maybe a V, a shear diagram line, V in kips, and then the moment in kip feet. Yes, a question? Okay. A would be your axial load, or your normal force. So, we would have a constant axial load of negative 4 kips. So basically, you can have axial load diagrams just like you can have shear diagrams, and for columns where you have different loads applied along the different vertical loads applied at different points in the column, it would actually be non-constant. For example, if I had a column that spanned between multiple stories, the load would be increasing as you went down the column, or actually in all columns even the load is going to be increasing as you go down, if nothing else from the self-weight of the column. If you think even if a column that's not supporting really any axial load, external axial load, let's say you had just a flagpole or something like that, literally just a big flagpole with no wind blowing. in that case, you would have 0 axial load at the top and a linearly increasing axial load until you reached the bottom. And the slope of that line would be the weight per foot of the flagpole. Now, we don't usually consider flagpoles in the design as structures, but you can consider that a very simple structure if you want. Although I'm glad that on your last homework we had to go out and find a structure and analyze load path. I'm glad that no jokers decided to look at a flagpole. So. Would have been a good idea, but I would have probably put up some objections to that. So we have the shear now in kips. So the very first thing that's going to happen is that the shear is going to bump to the left in this case to a value of positive 25 kips. Then between here and here, the shear is going to be constant. It's going to be constant. Then it's going to drop down by a value of 10 to a value, it's going to drop down by 10 to a value of 15. To a value of 15. And then it's going to remain constant until the end of the beam, or sorry, the end of the column. And then it's going to go down to 0 because of the end force here. Then, to get this, and this would just be positive shear throughout, although, especially when you start having things that aren't oriented horizontally, the definition of positive negative shear really comes down to your sign convention. Now, the key to, of course, remember, we want to recall our area functions. So we need to remember that m is the integral of v dx, or at least the change in moment is, and that the slope, dm dx, the slope of moment is equal to shear. So to get the moment from here to here, we're going to start at 0. And we're starting at 0 because there's no end moment on this column. And we know that the area under this thing is going to be 25 times 4, so it's going to increase by a total of 100, and it's going to do so parabolically. So it's going to parabolically increase to 100. And if it was going to increase in a very strange way, I could say it's going to paradoxically increase, but maybe that's just every one of my lectures. So, wow, that's an English joke. Wow, that's really bad. Okay, anyway.
Can you explain why it's increasing parabolically?
Okay, the question is, why is it increasing parabolically?
Isn't shear constant?
Okay, actually, no, wait, sorry, not parabolically, it's linear. You're right, thank you. I guess it is increasing paradoxically. Yes, so it is increasing. I'm too used to constant distribute. I'm too used to distributed loads. Yeah, so it is going to be increasing linearly. Thank you. Because the integral of a constant value function is a linear function, so it's going to increase to 100. And then the area under this, 15 times 4, is going to be an additional 60. So it'll increase linearly, but at a slightly shallower slope, up to 160. 160 here. Alex, I'll put a dot there to indicate that we're changing slopes. Uh-oh, I didn't quite nail it, so that's okay. We'll just move the point. Okay, and then the end force, the end moment, or not the end force, not the end moment, sorry, the end force that's being transferred, or actually the end moment, sorry. The end moment that's being transferred through the joint will then drop this back down to 0. So your shear and bending moment diagram should always find their way back to 0. Okay, questions on that? Yes?
Is there any relationship between the axial load and shear and moment as we have with shear?
The question is there any relationship between axial load, shear, and moment? And the answer is, as long as it's centrically loaded, no. If there is any kind of non-centric loading, for example, or a centric loading, for example, if the thing is, if the column were bent, for example, and then if you had a column like this, like a really bent column, not something that bent, but if your column is bent, when I apply an axial load like this, I in turn generate a moment. Or if it's not lined up with a centroid of the member, then you would also get loading, or also get moment. But as long as everything is ideal and purely axial, the axial force won't generate shear or moment. Although, the axial force in one member can generate shear in another member, but purely within one member, no. Yes, question?
Yes, why doesn't the distributed load on the top contribute to the axial load?
Okay.
Is it just negligible?
The question is why doesn't the question was why doesn't the distributed load on the beam contribute to the axial load here? And the response or the answer there is it does. It does. It's just baked into. It's already baked into the reaction here. It's already baked into the reaction. So, and it's also already baked into our end force here. Okay. All right. Questions on that? Yes.
You might have already covered this, but for the AX or whatever, how did you get -4 instead of positive?
That's a good question. How did I get -4 instead of +4?
The actual
Compression. Yes, the answer is it's compression. Okay. All right. Other questions? Okay. Now I want to get the shear and moment diagram for the beam, and that's going to be fairly trivial. There's not going to be. I'm going to go ahead and draw this underneath here. I'm going to draw it. I probably should have left myself a little more space above here. That would have been ideal. Usually, how I draw this if I have a little more space is I draw the axial force and the shear and then the moment above these. I'm just going to draw them down and to the right a bit so we can be clear that we're not talking about the same structure, but I can still fit it on the same page here. So I'm going to have the axial force in kips. Then I'm going to have the shear in also kips, or also in kips. And then I'm going to have the moment in kip feet. In kip feet. Okay, the axial force should be fairly simple. What's the axial force? Yep, there is no axial force in the beam. Although you have to be careful when I say beam and column because this is both a beam and a column. Yes, it's physically a column. Its primary function is to support vertical load, but it's also supporting a great deal of bending. So we would call this a beam column. Then, if I look at the distributed force, it's a uniform distributed force. So that means the shear. Well, we're going to start with with our. If we go back to our free body diagram here, we effectively have a vertical reaction on the left of 4 kips, which means we're going to jump up to 4 here on the right-hand side to a shear of +4. Then we are going to drop along at a slope of -4 kips per foot squared until we get down to the final value at the end. So the total amount, again, we have to remember our area relationships. The total area under this is going to be 4 times 10, which is 40. So it's going to drop down a total of 40, and 4 minus 40 is -36. So this is going to drop down to -36. -36 kips. And it's going to drop down linearly. Why is it linear? Because it's a uniform distributed load. Yes, and the integral of a uniform function is of course a linear function. Now, here's where it gets fun. The moment. Okay, so the moment is immediately going to jump up to 160. This is because of the end moment on the right. Now, I do want to take a note to look at the direction of this. So notice this MB here, this MB is a negative moment. It's a clockwise moment applied to it. On the beam, a clockwise moment is being applied to the outside of it, and that's effectively a negative moment. But as we've discussed before, if you apply a negative moment to the outside of a beam, it's going to cause an opposite internal reaction. So that means the internal moment on our beam BC is going to start out at +160. Then, let's see, it's going to increase. Now we do need to know in order to do these area functions properly, I would need to know the dimensions on here. So thankfully this isn't that difficult. This is just going to be what? This is going to be, well, it's only going to take 1 foot of beam for this thing to drop down, correct? That makes sense? It's only going to take 1 foot of beam for this thing to drop down to 0 because it has a slope of 4 kips per foot. And then that means this length is 9 feet. And we would need those dimensions in order to find the area under the triangles. Then the area under this triangle is 1/2 base times height, or 2. So that means up to this point, it's going to increase parabolically. Finally, have something properly parabolic. It's going to increase parabolically to 162. And how did I know to draw this as a concave down parabola? How did I know that? In other words, how did I know it was going to go like this instead of like this? Because the slope is decreasing. Yes, we know the shear, again, is the slope of the moment function, so the slope should be decreasing as you go along. Then here, we know the slope is going to be getting increasingly negative, and the area of this, 1/2 base times height, when the height is -36 and the base is 9, you will get a value of -162, which means this thing is going to drop right back down to 0, and it's going to do so parabolically, with an increasingly negative slope. And this ends up having positive bending throughout. Nice, positive, happy bending. Think positive. All right, other question, or any questions on that? So the basic process was we drew our, we looked at an external free body diagram. We took all of our internal, we found all of our forces at the joints, and then we went and found our the forces in the joints, and then all of the external forces. We found the external forces, with those we found the internal forces, then we found the shear and bending moment diagrams in both the beam and the column and the axial diagrams as well. Yes?
Axial load diagram.
The axial load diagram, again, for the column, it's just there is a 4-kip vertical force on it, on this one here. There is no axial force on this beam. So, now it may be confusing. Doesn't this look like there's axial force on the beam? Is that what you're thinking? It looks like there's axial force on the beam here, but if you actually go back to the separated bending moment diagram, we saw that there actually isn't any axial force on the beam here. This bx here is equal to 0, and there's no other x force on the beam. And so there is no axial force on the beam itself. And now I'd like to continue with another example of frame shear and bending moment diagrams. So my second example is going to be a frame that is not statically determinate as a single rigid body, but, well, because it has internal pins, we'll see that this actually is statically determinate. So example 2 here. We will be able to solve this without having any information about the member cross sections, materials, etc. So let us consider a frame here. Let us consider a pinned frame, and let's say it's a fixed support here and a pin here. And then let's say it has a beam here with another pin joint, and then a column and a pin joint here. Then we're going to have the following geometry. Well, actually, let me get the loads here first. I'm going to have a horizontal load of 0.8 kips per foot, or 800 pounds per foot if you prefer. Uh, 0.8 kips per foot. And then 2-point loads of 6 kips and 3 kips. All right, so we have this, let's see, that's going to be 8 feet, 8 feet, and 8 feet. So all this is given, and we have a height of 15 feet here. So all of this is given, and I want to find the V and M diagrams. Oh, sorry. Find the V and M diagrams. The shear and moment diagrams. All right, so the first step is going to be to break this into pieces. We're going to break this into pieces and do an exploded view, look at all the internal forces, then solve for the internal forces. Again, we're going to be able to do this primarily because this is a statically determinate system. In another video, we'll put together something illustrating the method of calculating whether a frame like this is statically determinate based on the number of pin joints, the number of supports, that sort of thing. Okay, so on the next slide, I'm going to put together a exploded view showing all of the internal forces, and then we'll solve for those. So, oh, and let me give you the joint names. That would be important. It's fairly straightforward, though. It's just going to be A, B, C, and D. A, B, C, D, but going clockwise around like that. Okay, so first we're going to have column AB. Going to have column AB. Then we're going to have beam BC. And then we're going to have column CD. So this, and let me show the forces on here, or the reaction forces. So first, I know that I have, well, actually, let me go ahead and draw the forces on here, because this is going to be how I kind of assume the initial direction for my forces. So I have 0.8 kips per foot on this. And then the reactions are going to be AY. Let's say AY. And then I'm going to have AX. I went ahead and assumed this thing was acting to the left because I see this large horizontal load here, so it's reasonable to presume that this is acting to the left here. But that may be, depending on how things interact, that may not be the case. Then, let's see, I'm also going to have an MA here. And then in turn, perhaps I'll also here. Oh, and this here. I can't actually figure out this horizontal load. There's going to be a horizontal thing here, a horizontal force transferred through joint B, but I can actually get that directly without doing a lot of calculations, and you'll see why first. So first I'm going to have dy, and then I'll have dx. Then I'll have my 6 kip force and my 3 kip force. And then I'll have a by. I'm going to assume this is acting upward on this beam, and this was acting upward on this beam, or this end of the beam, or this joint. And then cy here. Now, again, I can assume whatever direction I want. I just have to assume compatible directions. So if this by is going upward, this by must be going downward. And this, in turn, let's see here. What else? Here, you know, I think I'm just going to go ahead and solve for the reactions on this beam, or on this column, and that'll allow me to get to the directions of all these things. So here, let me go ahead and just say, okay, let's just assume Bx was acting to the left. And then to the right here. And if Bx is acting to the right here, Cx would have to go to the left here, and Cx would have to go to the right here, and Cy would have to go down here. Again, you can assume whatever direction you want, you just have to assume compatible joints. So, okay, question, why didn't I have a moment on these joints? Because they're pins, yes, by their very nature, by definition, pins cannot transfer moment between them. By the very definition, pins cannot transfer moment between them. All right, so let's work through this. Now, let's see, so I'm gonna start here. Oh, let's see, what should I do? Something like this. Let's do a sum of moments about point D on this beam here, so, or this column here. So if I do a sum of moments about joint D, and let me call this, I'll just call this 1, 2, and 3. So that way I can put a subscript in each of these as well. So that would be the sum of moments on object 1 about joint D. And so that would equal then, let me go ahead and put my dimensions on here so that's easy to tell. This would be, let's see, that's going to be 15 feet. This is going to be 15 feet, and then 8, 8, and 8 feet. And 8 feet. So if I do a sum of moments on object 1 about point D, I'll get that Cx times 15 is equal to 0. So therefore, Cx is equal to 0. Why didn't dy, dx, or dx, dy, and cy appear in that moment calculation? Exactly, their line of action passes through point D. Good. Stay, review from statics. So I know that Cx is equal to 0, which means Cx is equal to 0, which in turn, if I look at this beam here, what can he tell me about Bx?
0.
It's also 0, yes. Look here. There are only 2 horizontal forces acting on this beam, so if Cx is equal to 0, therefore Bx is equal to 0. Now, these could have non-zero values, but only if B and C both had equal and opposite values. As long as there are no external, there are only 2, again, there are only 2 horizontal loads on this beam, or only 2 horizontal reactions, no external loads. So if one of these is equal to 0, then both of them are equal to 0. And that's equal to 0 there as well. Okay, so we have that. That's some progress. Okay, so what else could we do? Let's see. We could do a. Oh, let's see. Let's do let's go back to object 1 again. I kind of like working with the simpler objects first. Or let's see. It's always debatable where you start on these things. So let's see. We have that. Then. Let's see, Bx equals Cx equals 0. We have that. Then, about B, some moments about here. Yeah, let's do that. Let's get Cy. That would be a good thing to do. Let's do a sum of moments on object 2 about, say, point B. Moments are usually a very good way to really cut through the clutter. So, what are we going to have? Well, if we look at this, we're going to have minus 8 feet times 6 kips. So I'm taking the moments about this beam here, this free body diagram here, about point B here. So minus 8 feet times 6 kips minus 16 feet times 3 kips, and then plus 24 feet times Cy equals 0. And then this comes to Cy is equal to 4 kips. So Cy is equal to 4 kips. So this Cy is equal to 4 kips, which means this Cy is equal to 4 kips. And in turn, dy is also equal to 4 kips. I could write out an entire equation for the sum of forces in the vertical direction, but I think for a simple case like this, it's fairly straightforward that if the only vertical force acting downward is 4 kips, then the only vertical force acting upward has to also be 4 kips, just by a very simple equilibrium. Okay, then I can look at a sum of forces in the vertical direction on here to get my by. Oh, and also here I can also say that dx here has to equal 0. Dx here has to equal 0 based on the same horizontal force equilibrium on this member here, on member CD. Okay, then, so we have this and we have this. Let me do a sum of forces in the vertical direction, and I'll do this in object 2. So sum of forces on object 2 in the y direction. Now, if I wanted to be more proper, I'd probably put AB here, or BC, or CD, but I have a simple 3-member thing here, so I'm trying to keep my notation to a minimum. So what am I going to have? I'm going to have BY plus CY, and then minus 9 is equal to 0. Here, again, the 6 plus 3, that's where I got the minus 9. And therefore, if I put in, let's see, also that leads to, I already know the value for CY, BY plus 4 kips minus 9 kips equals 0. Therefore, BY is going to be equal to 5 kips upward. Or just 5 kips. Whether it's upward or downward will depend on which member you're looking at. So this is going to be equal to 5 kips here, and this BY is also going to be equal to 5 kips, but 5 kips downward. Okay, so we have that. Then, looking at this beam here, or this column here, well, it's a beam and a column, it's a beam column. Again, in structural engineering parlance, anything that has a bending on it is going to be a beam. So this thing has horizontal loads, or transverse loads would be a better way of stating that. So yes, this is actually both a beam and a column, but usually we still refer to things that are vertical as a column, so I'm being a bit sloppy with my language. But anyway, I just see loads like that. I'm like, oh, that's a beam. So, okay. Now, one of these, we still have 3 unknown forces. One of these we can very quickly take care of. Which one? AY. Yeah, AY, very good. AY, that's going to be, now AX isn't going to be that much difficult, that much more difficult either, but AY is going to be very easy to take care of because I can just do a sum of forces on the vertical direction. So if, in other words, if there are no other vertical forces on this member, so therefore a sum of forces in the vertical direction will show that BY is equal to AY is equal to 5 kips. Here. Then I can do a sum of forces, in the horizontal direction, here. Sum of forces in the horizontal direction, let's see. That's going to be negative AX plus 0.8 kips per foot times a total length of 15 feet. And then minus BX, but that's equal to 0. And this all equals to 0, and that leads you to that AX is equal to 12 kips. So AX is exactly equal to 12 kips. Are we done? We have all our forces. But we don't have that moment. Yes, we can't forget the all-important moment. You don't want to forget it because, do you know why? Because it's quite momentous. Oh boy. All right, so that is really bad even for me. Sum of moments about A is going to be equal to 0, and this is, I'm going to, you know what, to be consistent, I should probably put a 3 here and a 3 here to show I'm doing the sum of moments of object 3 about point A. And that's going to be equal to 0, and that will be negative 12 kips, that's the equivalent point load of our distributed load, times a moment arm length of 7.5 feet. Again, the centroid of the distributed load is right at halfway. It's right at halfway along the column's height because it's a uniform load. And then plus MA is equal to 0, and therefore that leads us to MA is equal to 90 kip feet. So MA is equal to 90 kip feet. MA is equal to 90 kip feet. Now, while you write that down, I wanted to sort of go back and talk about this a bit. So, one thing to keep in mind is one thing I really like about these examples is it really gets at the heart of the relationship between member internal forces and end conditions. In other words, if you really want to know something about a member, know how it's supported, know what its ends conditions are. Once you know once you know the end forces and the end moments and the axial forces, if you know what any loads are applied to the outside of it, you can very easily solve for all of the internal forces. The real difficulty in frames is solving for those member end forces. But once you have those, everything else is fairly straightforward. Yes?
Could you get the moment around B and get the same answer?
Okay, the question, are you talking like on object 3 here?
Yeah.
Okay, on this column here. The question,
To get MA?
yeah, the question was, if I did a moment about joint B, would I get the same answer? Yes. Yes, you absolutely would. If you did it right, of course. but that's the same as true as everything. But let's think about that. If we did that, what would we have? We would have AX times 15 feet. You know, why don't we just demonstrate that? Let me do a side calculation here, maybe a little bit in, I don't know, some orange, just to illustrate that it's a side calculation. Let's try that. Let's do a sum of moments on object 3 about joint B. Counterclockwise positive. Let's see. Well, my BY and BX and AY won't generate any moment there. Then, let's see. I will have, in the clockwise direction, so that'll be negative 12 kips times 15 feet, moment arm length of 15 feet. Then, here my distributed load is going to be generating a positive moment, so plus, that's going to be 12 kips again, the equivalent point load of that distributed load. 12 kips times a moment arm length of 7.5 feet, and then plus MA. Wait, what's the moment arm length for MA?
15.
No, feet are included.
Exactly, so half the class responded 15 and then half responded correctly. Sorry. No, it's a trick question, of course. So as we've already discussed before, I know it's early in the morning, but as we discussed before, this is already a moment, it's already a couple. We don't need to, this is a good in the statics review. We of course do not need to include any moment for, or any moment arm for our moment that's already a couple, or a couple that already has the moment arm baked in. Okay, so we have that. Let's see, what is 12 times 15? What is that? That's, let's see, that's going to be 4 times 4 is 60, so 180, right? So negative 180, and then that's going to be plus 90, right? Actually, no, it's yeah, like that, and then plus MA is equal to 0. So then we have negative 90 plus MA. Plus MA is equal to 0, and then MA is equal to 90 kip feet. So again, regardless of what point we sum moments about, we will get the exact same moment. And in fact, as we learned in statics, that doesn't even have to be on the object. I could sum moments about point C if I wanted to. I could sum moments about point D if I wanted to. I could sum moments about a point 1.7 light years to the right of here. It doesn't matter. Now, of course, you can sum moments about any point, but of course there are some points that are more convenient than others. If you wanted to sum moments 1.7 light years away to an angle of 45 degrees to this, or even better, if you really wanted to have some fun, you could sum moments about a point 1.7 light years into the page. So this would then be a three-dimensional problem, and you'd have to do all this with cross products. You could do that, but I don't suggest you do that on the exam, because that's going to, well, consume a great deal of time. So, I mean, you could do it, but, you know, if you really want to do that, I'm not going to stop you. But anyway, you can, of course, sum moments about any point, but of course there are points that are more convenient. Usually points on the object are more convenient because then you can take advantage of the fact that objects or forces that have their lines of action passing through that point will not generate any force there, any moment there. Okay, so what I'm going to do next is I'm going to draw this frame out and find its shear and bending moment diagrams via the method of inspection, or by inspection. Because again, once we have the member end forces, we can figure out the rest fairly easily. Again, the whole point of finding the member end force is that you can then isolate or analyze each individual beam and column as an isolated object. And once you know the end forces, you can get the shear and bending moment diagrams fairly quickly, or fairly easily. Well, relatively easily. So my A, V, and M diagrams and I'm going to try to squeeze these all into one slide here. So I'll have this column, this beam, and this column. And then I'm going to show the internal forces, or not the, sorry, not the internal, the external forces. 12 kips, 5 kips, and 90 kip feet. And going back, let's see, that was BY was 5 kips downward there. So 5 kips, 5 kips here, and 5 kips here. And we had no horizontal load on the beam here. And then on the other end of this, we had a 4 kips upward here. Sorry for jumping back and forth. 4 kips and then 4 kips downward here. Then we have 4 kips upward and no horizontal force on this column here. Then I'll go ahead and show my my external forces, the 6 kips and 9 kips, and 9 kips, and then my distributed load here of my 0.8 kips per foot.
Isn't it 6 kips
6 kips and
and 3 kips?
3 kips. Oh yes, sorry, yes, 6 kips and 3 kips. I was in the correct order of magnitude. Hey, it's close enough for astronomy. That's a cosmology joke. Ask an astronomer. Anyway, 0.8 kips per foot. 0.8 kips per foot here. So I think I'll start with the easy one because I'm lazy. So first I'll write down the A here. Get my A diagram. And then maybe I'll have my V and my M. This one's going to be nice and easy. Let's see here. So, what is my A going to be? What is my axial force going to be? It's going to be 4. Is it going to be 4? It's actually going to be negative 4. I probably should put kips here, and kip feet. Yeah, it's going to actually be negative 4. So negative 4. Again, this is all in compression. This is a compression member, not a tension member. So we want to make sure our shear, our axial force, is going to be negative. Then what about the shear on this thing? There is no shear. Yeah, there is absolutely no shear on this, and that is because there is no transverse force. There's not going to be any transverse force on this column. Again, transverse force referring to force perpendicular to the member's axis. There is no shear, and there is also no moment in turn because there's not any end moments. There's no couples on the thing. There's no transverse loading. So therefore, the moment is also equal to 0. No moment. Okay, then on the beam, let's go to the beam. First, maybe I'll get the axial force. I'll hide the axial force way up here because this is going to be kind of cramped. My axial force, this one here is going to be 0. I'm not going to have any axial force because I'm not going to have any axial force because there's no axial force, or more specifically, on this beam there are no horizontal forces applied to this. So the axial force is going to be 0. And on these, I just kind of like to put a horizontal line through or a line right along the axis, and then a 0 on the axis to indicate that, but that's definitely just a stylistic choice. Then I'm going to have my shear diagram, and I'm going to try to squeeze in the moment diagram, but if not, I can write it over here. Then the V, the the shear diagram. Let's see, let's consider this. The first thing that's going to happen is we're going to pop up to 5 kips. Then we're going to remain constant until the 6 kip force, at which point we're going to drop down to -1 kip. Then we're going to remain constant over to the 3 kip force, at which point we'll drop down another 3 to -4, and then we'll remain constant until the 4 kip force, which will bring us back to 0. And that will be positive and negative shear here. So a maximum shear value of 5 kips and a minimum of -4. Then I think I do like to, if I have enough room on a page, if I'm doing this on an 8.5 by 11 sheet, or actually I probably should have just drawn this further down or whatnot, but that's okay. Ideally, I do like to keep everything lined up. I don't think I'm going to be able to quite squeeze that in there, so I'm just going to write the shear diagram here. Ideally, this would be down here to keep everything lined up. So, moment diagram. Yeah, the moment here. So the moment's in kip feet. And this is all going to be based on areas. So our initial moment is going to be 0. Our initial moment is going to be 0 because we have a pin joint at the end and no couple or something like that. So in this first region here, before the 6 kip force, the area of this, remember these are 8 feet, 8 feet, and 8 feet. So the area of this is 8 times 5, or 40. So we're going to increase linearly up to 40. Why linearly?
Shear is constant.
Exactly, because shear is constant. The shear function is a constant value function. Therefore, the moment will be the integral of that, or a moment function. Then the area under here, -1 times 8 will be -8, and 40 minus 8 is 32. So we'll drop down to 32. 32 here. And then finally, the area of this 8 times 4, or 8 times -4, is -32, and that will bring us back down to 0. And so we do have positive moment throughout, positive bending in the beam here, in our vertical or in our horizontal beam. All right, questions so far? Okay. So I'm going to do the same thing here, and the first thing I'm going to do is start with the axial force. Let's start with the axial force. And this axial force, we're going to have 5 kips downward and 5 kips upward. Well, actually, that's a free body diagram. Let's just go to the axial force diagram. So this is going to be 5 kips negative. And this is our axial force diagram in kips. Then I want to have our shear diagram. And this diagram is going to bring shear excitement. Again, that one's bad even for me. And so the shear here is going to be in kips. Then we're going to initially start out at positive 12. We're going to initially start out at 12. And then it's going to continue linearly downward to 0 because we don't have any horizontal force here. So we start up at 12 here, and then we decrease linearly downward to 0. Sort of linearly. Linearly, mathematically, not so linear on my drawing. Then I'm going to need a moment diagram. And this one's not going to be too bad. I will be able to squeeze this one in. If I can manage to draw a straight line. Straight enough. And this will be my M in kip feet. My moment in kip feet. And let's see, at the end here, I'm going to start down at -90. Why did I start at negative? Yes, see, we have that, that end moment. And if you think about this, this is a positive moment applied to the outside of the beam, right? This is a positive moment applied to the outside of the beam, which means the internal moment that's resisting that is going to be negative. We always have to keep that in mind. Positive moments, or positive point moments at least, when applied to a beam will cause the internal moment to decrease. So that's why we're going to start our moment down at -90. And since this is a linear function, we know that, well, let's first get the area of this. 12 times the height of 15 feet. Let's see, was it 15 feet? No, it was, yeah, sorry, 15 feet. 12 times 15 feet times 1/2, that's going to be 90. So this is going to come right back to 0. Now, the question is, what kind of curve is it going to be? Well, I know the integral of a linear function is a parabolic one. So the question then becomes, is it going to be a parabola like this? Or is it going to be a parabola like that? It's going to be a parabola like this. And again, because the shear is the slope of the moment function. Here the shear has a value of 0, so its slope should be getting closer to 0 and at 0 at the end. And then here the shear has a non-zero value and is much greater, so it should have a steeper slope here. And so overall, our beam has a negative bending moment here. Our column has a negative bending moment. Now, I would like to give a note on sign convention. How do you know, for beams, it's very easy to see what is positive moment, what's positive direction, positive shear, that sort of thing. You usually just want to make sure you're, for horizontal beams, it's fairly easy. You just orient it such that a positive bending makes it actually bend like this. The question is, how do you do that for columns? Well, for columns, generally how you can just handle it is, usually I always label my columns like column AB, column CD, that sort of thing. But basically, whatever your naming convention is, you're basically going to have to define a 0 end of the beam. As if you're doing this by integration, you would need some point that was the 0x value, and in turn, that defines what your overall positive and negative bending moment are. All right, questions on this? Okay, that'll conclude this video that'll conclude this lecture on shear and bending moment diagrams of frames. Thank you for watching. We'll be back again, and as always, thank you.